Hello everyone, I'm Rongchen from Tsinghua University. Today, I'm glad to show our recent work on generating interval counterexamples for loop invariant learning and using them to accelerate the program verification. Let's start with some information about loop invariants. A loop invariant is a property that always holds when a program enters, iterates, or exits a loop. A loop invariant is a relatively regular upper approximation of the actual program space, which can effectively assist in proving the properties for programs containing loops. However, the generation of loop invariants has been a challenging problem for a long time. Data-driven black box loop invariant learning has emerged in recent years and shows it's promising. Our work is based on such a background. A typical black box loop invariant learning framework contains two main parts. One is a constraint solver-based teacher, and the other is a classifier-based learner. First, the teacher encodes the given program combining with the current hypothesized loop invariant into SMT's constraints. The initial value of the hypothesized invariant is true. The verification condition is generated and delivered to the solver for checking. If the checking passes, the current hypothesized invariant can successfully prove the program property assertion. Otherwise, the teacher will give a program state counterexample. If the program state counterexample can correspond to an actual program execution path, we will indicate the program assertion failed. Otherwise, we will add such a fake counterexample into a counterexample set and deliver the set to the learner for the further invariant modification. There are two types of program state counterexample when learner modifying the invariant hypothesis. One is the reachable program state but not included in our invariant hypothesis. We call them positive counterexamples. The other is the program state in current invariant hypothesis but may cause the failure of the property checking. We call them negative counterexamples. The goal of invariant modification is to incorporate all positive counterexamples into the loop invariant hypothesis and to remove all negative counterexamples from the hypothesis. Here we use the decision tree as a learner classifier. In this example, according to the optimal split theory of decision tree, two kinds of program states come into this situation after sleep. The upper left part contains only negative examples, so we do not need to deal with them anymore. The below right part still contains two kinds of examples, and we need to continue to split them. Finally, we get such a classification result. We can use the predicate of the positive examples as a new modified loop invariant. Next, let me introduce our motivation. In the left program example, the precondition of variable x and y are limited ranges. The loop condition is written in loop body. If x is greater than 0, then x will minus 1 and y will plus 1. The verification target is that the variable y should be in the range of 0 to 3 of the loop. Suppose initially our loop invariant hypothesis is true. Of course, the loop invariant is not sufficient because it cannot prove the assertion after the loop. Assume the SMT solver return a program state x equals to 0 and y equals to 9 as a negative counterexample. We add it into the counterexample set, which is initially empty, and then ask the learner for a new invariant hypothesis. The learner modifies the invariant hypothesis to false. In next round, the loop invariant is false. We find that the invariant cannot include all reachable program states. Assume the SMT solver returns a program state x equals 2 and y equals to 1 as a positive counterexample. We add it into the counterexample set and ask learner for new invariant hypothesis again. The learner modifies the invariant to y less than or equal to 8. Similarly, with the generation process of the first negative counterexample, y less than or equal to 8 cannot prove the assertion after the loop. The SMT solver may return a program states x equals to 0 and y equals to 8 as a new negative counterexample. We add it into the set and ask the learner to get a new modified hypothesize invariant again, that is y less than or equal to 7. When we analyze this process with the invariant hypothesize y less than or equal to 7, the SMT solver similarly returns a negative counterexample x equals to 0 and y equals to 7 again. During this learning procedure, we keep finding the similar negative counterexamples until reaching the boundary of negative counterexamples, which is x equals to 0 and y equals to 4. Actually, we notice that the negative counterexamples generated here have the same reason. We do not hope we always encounter this kind of same and redundant iterations which often cause a lot of time overhead during the verification. We think the main reason of this similar counterexample is that the counterexample given by constraint solver is a single program state and it is information limited. So we want to discover these commonalities in counterexamples and generalize a single program states to a set of program states such as x in the range of negative infinity to infinity and y in range of 4 to infinity. We call this kind of counterexample interval counterexample. There are two core issues in our paper. The first is how to generate a generalized interval counterexample, and the second is how to learn an invariant using given interval counterexamples. Now, let's consider the first question. We use the previous example again. Suppose the current hypothesized invariant is true. We use the invariant to construct the verification condition for the post assertion, which is true implies y greater than or equal to 0 and y less than or equal to 3. We can easily simplify it into y greater than or equal to 0 and y less than or equal to 3. We now introduce the first generation method, variable elimination. Assume that the SMT solver return the counterexample x equals to 0 and y equals to 9. Consider the conjunction of the verification condition and the valuations in counterexample. Obviously, the whole formula is unset. We treat the verification condition as a necessary constraint and x equals to 0 and y equals to 9 as optional constraint, and query the SMT solver for the unset call. The unset call should be y equals to 9. So we think we get a generalized interval counterexample, which is x in the range of negative infinity to infinity, and y equals to 9. In the figure, we can see the original single program state counterexample has been extended to a line-shaped program state set. It's clear that the variable elimination method is rough and in many cases cannot be used. Here we propose the second generalization method, boundary constraints. The original intention of this method is to use several predefined distance constraints to get a feasible generalization boundary. For convenience, the predefined distance here only contains two values, 0 and 5, for two optional constraints x equals to 0 and y equals to 9 in previous onset call. We use 0 and 5 to extend them into 8 optional constraints. Here, note that 4 equals to 9 minus 5 and 14 equals to 9 plus 5. Then we call the solver and we get the onset call y greater than or equal to 4. So we say our generalized interval counterexample now is x in range of negative infinity to infinity and y in range of 4 to infinity. In this figure, we can see that the original single program state counterexample has been extended to a block-shaped program state set. In actual experiments, we found that the results of unset call are often not unique. In the situation just now, both the constraint y greater than or equal to 9 and the constraint y greater than or equal to 4 can be returned as the unset call. Obviously, we prefer to get the latter one. However, which constraint should be returned as a result is often related to the decision strategy of the constraint solver, and we can hardly promise. Therefore, we hope to rearrange the optional constraint of the onset call. We divide the variable ranges into corresponding intervals. We hope we can find all the intervals existing program states which cannot be generalized and dig them out. Then the remaining intervals are all intervals that can be generalized. In above example, we arrange the constraint as the formula shown. We call the onset call and get the unique onset call is the negation of y less than 4. So we can get a precious generalization result y in x in range of negative infinity to infinity and y in the range of 4 to infinity. We use an example to explain how we adapt the decision tree to interval counterexamples. The core points here are whether and when the decision tree splits can cross the interval examples. We design a strategy where we first look for the best split which do not cross any existing interval examples. If we cannot find such a split, we will allow the crossing and then find the best split. The reason for this strategy is that we think the program states in interval counterexamples are from the same generalization, and the program states will have potential associations with others. We hope to keep these associations during the decision tree split. Consider the example. There are 5 interval counterexamples. Example 1, 2, and 4 are positive examples. 3 and 5 are negative examples. We hope our decision tree can make a correct split. First, according to the no-crossing idea, we get a split at position x greater than or equal to 0. Now the left part only contains positive examples and no longer need any operation. We continue to split the right part. However, the right part does not exist a no-crossing split because the distribution of the interval examples. We make the best split along in the crossing, which is x greater than or equal to 2. We can find the split across in the example 3 and deliver it into 2 sub-examples. 2 signs of split exist 2 kinds of examples, so both 2 signs need further processes. In left side, we get the best split y greater than or equal to 1. In right side, we get the best split y greater than or equal to 3. Put all the split results together, and we can make the disjunct of all parts which the decision tree predicts positive as the final invariant. Based on existing ICE framework, we implemented 3 generalization methods for interval counterexamples and a decision tree to support the interval counterexamples. Total 94 benchmarks come from 2 parts, 55 are from existing ICEDT tools, and the other 39 are from 3 branches related to loops in SVConf 2019. Our first experiment compares the performance between 3 generalization methods we proposed and the existing ICEDT baseline. In the table, the colon SO represents the number of problems solved. Colon R represents the total number of runs. Colon T represents the total time. Colon TC represents the time consumed by constraint solver. Colon TL represents the total time consumed by invariant learner. We can see that our three methods have significant performance improvements comparing to baseline. Also, our methods solved one more cases than baseline. Among our methods, the boundary generalization and the digging generalization are better than the variable eliminations. These two methods have more than 40% of improvement on both round and the total time. The purpose of the second experiment is to independently verify the performance improvement from the interval decision tree. We extract the representative information of each interval counterexamples, including their boundaries, their center position, and use the several discrete state counterexample to describe these features. We conduct the comparative experiment, and the cumulative rounds is shown in the figure. It can be seen that on total number of rounds, there are no particular difference between interval counterexamples and discrete program state counterexamples. However, does the similar number of rounds means our interval decision tree brings no improvement? Of course, no. We found the time difference between two methods is quite significant. The distribution of total time and learning time is shown in figure. The main reason for such a distribution is that when we use discrete program states counterexample to simulate interval counterexamples, more examples are needed to describe the future. This rate in our statistics is 5.7, so the decision tree for discrete points needs to process a large data scale of examples, and this is why the round numbers of two methods are similar, but the time is quite different. Finally, let's make a summary of our main work. First, we proposed a data representation called interval counterexample, which can represent a set of counterexamples from the constraint solver. Second, we proposed three different interval counterexample generalization techniques. Third, we improved the decision tree algorithm to adapt the interval counterexample. Fourth, we complete a prototype. Compared to the existing methods, we made more than 40% improvement on both learning rounds and total time. That's all of our presentation. Thank you for your listening. If you are interested in our work, welcome to discuss with us. Bye.